Hey, it's Mr. K doing a video for AP Physics 1, and we've got a momentum problem. This is a momentum problem that we were working on in class, and we ran out of time reviewing for the test, so here it is online. We have a 2 kilogram car moving at a speed of 3 meters per second to the right on a horizontal surface. As shown, it will collide with the second car if I don't know what the mass is. It's initially at rest, and the force of the collision is right here. Let's see what else is going on. As a result, the second car acquires a speed of 1.6 to the right. Assume that friction is negligible before, during, and after the collision. And let's see. Let's turn this music down a little bit. It says calculate the magnitude and direction of the velocity of the 2 kilogram cart after the collision. So this is a collision, and the title of the problem kind of already tells you what you might want to do. And so we're going to set up momentum. And so the momentum... that was weird. The momentum of the problem is initial is equal to final momentum. That's conservation of momentum. And remember that momentum itself is mv. So who has momentum before the problem? It's this car right here. So we're going to set this up. We're going to say it's got 2 mass, 3 velocity, and that's going to equal its mass times some velocity prime afterwards, plus the m that we don't know, and the v that we have here is 1.6 meters per second. All right. So seeing as how we have 2 variables in this problem, we can't really solve it this way, but we do know that there is a change in momentum. And if we know that there's a change in momentum, we can talk about the change as far as this goes. It's a force times the time. That's called impulse. And it will provide a change in the velocity of the car, so something like that. So where could we find a force for time? Well, that's going to be this graph up here. We've got a force, we've got a time. The forces are in kilonewtons. The time is in milliseconds. And kilo is going to be 1,000, milli is going to be 1,000th, so those two things cancel out. So if we're going to look at the impulse here, impulse is force in time, that's going to be the area of the shape. So we're going to look at the area of this triangle. It's got a base of 1, it's got a height of 10. Cut it in half, it's going to be an impulse of 10 kilogram meter per second. And or Newton seconds is one other way to say that. And so if I know that, well, hold on. Divided by 2, that's going to be 5 kilogram meter per second. And so I look over here and I say, all right, we know that the incoming momentum is going to be 3 times 2. It's going to be 6. So the momentum of this car is 6 meters or kilogram meter per second. And it's going to hit this other car. And when it hits the other car, it's probably going to slow down. And since it's going to slow down, that means I'm going to have some kind of negative change in momentum, and that's going to be negative 5. So I know we found out the change in momentum here, the impulse was 5, but you got to realize what's happening in the problem, and it's that the force graph is actually going to be the force graph that is for this object, and the negative of it would be the force graph for the other object, Newton's third law. All right, so the change in momentum is negative 5. That means my final momentum is going to be just 1 kilogram meter per second, or Newton seconds. And if I want to, I can now find the new velocity. Momentum is mv. That's equal to 1. The mass is 2. The v has to be 0.5 or half in order for that to equal 1. So the new velocity is 1/2 or 0.5 meters per second. And it turns out it's going to be positive. So it's still moving to the right. So this guy hits the other guy, reduces in speed, still moves to the right 1/2 meter per second. And then we can calculate the mass m of the second cart. Well, as we said before, that change in momentum does go to the second cart, and the change in momentum is going to be 5, I'll just write it this way, Newton seconds, or kilogram meter per second, as I was writing before. And we know it's positive because this cart was at rest, it's going to get some motion, it's going to gain this much momentum. Well, again, that change in momentum should be equal to mass times the change in velocity. Right? And the change in velocity is 1.6 because it was at rest. So 5 is equal to m 1.6. So 5 divided by 1.6 is 3.156. No, 3 divided by 1.6. Yeah. No, 5 divided by 1.6. Dummy. All right, there you go. 3.125. and it's going to be meters per second. All right, so that works out. It should make sense. Conservation of momentum does apply. So if we look at all the total sum of the momentum, we would say that this momentum over here was 5, the momentum over here should be 1, and that was a total of 6 in the beginning, so that works out. We can go down to the graph, and what I want you to notice is that with this graph, this graphing problem, you did not need to do A or B at all in order to go on and do C or D in this problem. So let's go ahead and read what it wants. It says, after the collision, the second cart eventually experiences a ramp, which it traverses with no frictional losses. The graph below shows the speed v of the second cart as a function of time t for the next 5 seconds, where t is 0, where t0 is now the instant at which the cart separates. So car came in, hit this car's moving off, and it's moving off at a speed of 1.6, which is noted on the graph, so that's 1.6. And this thing goes for 2 seconds, it slows down, and then it goes for another 2 seconds there, or maybe a second and a half. It says calculate the acceleration of the cart at 3 seconds. So at 3 seconds, we're talking about right here. And if we want to find the acceleration, if you forget what acceleration is, let's go back to your basic concepts. Change in velocity over the change in time. And if you look at the graph, this is a speed time graph or a velocity time graph if it's all positive. And we're just looking for the change in velocity over time. So you don't pick like the point in the beginning and the point in the very end. That would give you the average acceleration, I guess, for the whole thing. We want the instantaneous acceleration for this section here. And we would say, all right, well, I know that if I find the slope between these 2 points, that should be the same as the slope at that single point. So if I look, I know that this line is 0.5, and I go all the way up to 1.6. So that is a change of 1.1, and it's a negative change, negative 1.1, and it's going to take me from 2 to about 3.5 seconds to do that. So that's about 1.5 seconds. So I'm going to take 1.1, divide it by 1.5, and that's going to give me a negative 0.733 meter per second value. Okay, and so if I just double check, I go from 1.6 down to 0.5. Again, that's the difference of 1.1, and that takes me 1 second, 0.5 seconds, 1.5 seconds, and so that ratio, that should be the acceleration at that point. Now, for the next part, it says calculate the distance traveled by the second cart during the 5-second interval, so the whole thing. And we want distance, and we know that if we take a velocity and we multiply it by a time, we should get a change of position, because velocity is just change in position over a change in time. Now, our velocity does change here, but if we just look, velocity time, that's going to be velocity and time, that's going to be the area of this thing. So if we want to find the change of position, we should probably be looking at the area. And so what I'm going to do is I'm going to split this up into familiar shapes that are much easier to work with. Okay? And so if I work with these shapes, then I should be able to find the area quite easily. So at the very end, I have a height of 0.5, and I've got a bottom of 1.5. So what is half of 1.5? Half of $1.50, that's about 0.75. Okay, over here, I've got 1, 2, 3 squares as well, so that's going to be another 0.75. Here, this triangle is going to be a little bit different. The base is 1.5, and the height is going to be that 1.1 again. So, let's see. 1.1 is the height. The base is, what was it again? 1.5. I'm going to have to cut that in half. So, 0.825. And then over here, it's just this big rectangle. The base is 2, the height is 1.6. So 1.6 times 2 is going to give me 3.2. So I'm going to take each and every part of that and add it all up. And I get an area of 5.525 meters. So that's how far I should have gone in that time. Just kind of looking. That kind of makes sense. 5 seconds and an average velocity of around 1. So yeah, that should make sense. And then we got to do this last part, and it says state whether the ramp goes up or down and calculate the maximum elevation above or below the initial height reached by the second cart on the ramp during the 5-second interval. And so you got to think, what's happening to the speed of this cart? And so the speed of this cart is slowing down, right? And that's only going to happen if you go up a ramp. So that cart's down here, and it's probably going to go up a ramp some bit, and while it's on the ramp, that's when it's slowing down. So the answer of whether it goes up or down, it goes up a ramp, but we need to know how high up it goes. And so what we need to think about here is probably energy, because it's at a certain kinetic energy here, and it's at a different kinetic energy up here, and in between it probably lost some of that kinetic energy to the potential of the Earth. So the Earth cart system here, as this cart goes up, it's going to lose kinetic energy, and it's going to give back potential energy to that system. So if it wanted to go down the ramp, it'll gain it all back. So we really need to find out what the difference in kinetic energy is, because the difference in kinetic energy should be the change in the potential energy due to the height. All right, so we need to look at the speed before and the speed after. So the speed before is 1.6. So I've got this 1/2 m of the cart, 1.6 meters per second squared. So 1/2 mv squared. That's going to turn into, actually, this is my initial, right? So I got to subtract and find the difference. The difference would be my new velocity at the end is 0.5. So I've got 1/2 m, and I've got a 0.5 squared. And that's going to give me my difference in my kinetic energy. My kinetic energy goes down, all right? And then whatever I get that difference as, it's going to be my gain in potential energy, which is going to be just mg delta h. And so that should work out. Let's see, all the m's do cancel out. Everything does have m, so you can go ahead and cancel all those out. I'm going to take 1.6, we're going to square that, cut it in half, and that's going to give me 1.28. I've got a 0.5 squared, and I'm going to cut that in half, and that's going to give me my 0.125. And that should be equal to g, I'm going to use 10 for g, and delta h. So whatever this left side is divided by 10 is going to be h. So 1.28 minus 0.125 divided by 10, my height is going to be about 0.115. So if we're working in meters here, it's about 11 centimeters. So it goes up the ramp. Let's see. The ramp's about this tall right here. So that should work out. And that would be the end of the problem. There wasn't a lot of writing in this problem. Usually you have a lot more justification. So don't just focus on the calculation, but also be able to talk about what is going on in the problem. That's why I was trying to give a little bit of elaboration. If I didn't even talk and just solved it straight up, it would only take me a matter of minutes. But definitely explaining things takes a bit longer. So make sure you know how the momentum goes from one cart to the other, how we have conservation of it. Make sure you definitely know what the graphs mean. This one is a force time graph or impulse graph. This one is a speed time graph, and so that's going to be, well, let's see, it's a speed time graph. And if you find the slope of it, that's acceleration. If you find the area of it, you're going to have the position change. And you can always usually solve parts of the problem that are later on without solving the beginning, just in case you can't do the beginning. Partial credit is everywhere, so make sure you definitely try to get all those points. All right, we'll stop it here.